So we begin with lecture 11 of STAT 702, and we're going to look at the immediate generalization of the Poisson process, and that's going to be very brief before we get into chapter 10, where we're going to talk about Brownian motion, a very interesting stochastic process, a prototypical stochastic process in many respects, and we're going to talk about that a lot. But to begin with, let's just generalize the Poisson process with just the very first step in generalizing it. So we're going to talk about the non-homogeneous. So we saw that the Poisson process itself is a prototypical counting process. It has stationary and independent increments that follow the Poisson distribution, right? So basically that's what the Poisson process is. And what it does is that it is characterized by exponential interarrival times. So in interarrival times are memoryless in distribution, which is to be expected since you can begin the process at any point in time and you will see the very same probabilistic behavior. Another question is, can I go from homogeneity, right, in time, which is stationarity and independence, to non-homogeneity? And that's, of course, the very first next step to look at in generalizing the Poisson process. So the non-homogeneous Poisson process is non-stationary, of course, and it's a non-homogeneous within so the counting process n of t is non-homogeneous, is a non-homogeneous Poisson process with intensity function lambda of t with intensity function lambda of t, okay, if two is n of t still has independent increments. So it is really the stationarity that gets generalized. And what you have is the probability that any interval of length h, that two events or more occur in any interval of length h is again O of h, so negligible. The probability of having that is negligible. But that the probability of actually having one event occurring in a length, in an interval of length h is in fact lambda of t h plus O of h. So what we see is that now the left-hand side depends on t, and so does the right-hand side, right? So that immediately tells you that the stationarity assumption is not satisfied anymore, because for every single different t, so for any interval that starts at any different point in time, all right? So for instance, for the interval that starts at t0 plus h to t0, so let's say here, this is the interval t0 to t0 plus h, this is the interval t1 to t1 plus h, etc. They're all of length h, but for each of them, the rate at which the excuse me, the event will occur is going to be different. So for instance, for this particular interval, the rate is going to be lambda of t0 times h. So the probability of having one event in that length h interval is going to be lambda of t0 times h, whereas for this interval it's going to be lambda of t1 times h. So the stationarity assumption is indeed no longer satisfied in the non-homogeneous Poisson process. That's why it's called non-homogeneous, since the homogeneity of the time intervals is basically violated. Okay, so now okay. So just a few, so this is exactly like a Poisson process, but it's not stationary anymore. Okay. Now there are several interesting results regarding the Poisson process, the non-homogeneous Poisson process. I'm just going to state one of them. So if you let n of t and m of t be independent non-homogeneous probability non-homogeneous Poisson processes with respective intensities lambda of t and mu of t, and if we let n star be the sum of these independent, so these are independent Poisson processes, non-homogeneous Poisson processes, then the intensity function of n star of t is lambda of t plus mu of t. So if you take the sum of independent non-homogeneous, you get a non-homogeneous Poisson with intensity equal to the sum of the two intensities. And given that an event of the n star process occurs at time t, then independent of what occurred prior to t, the event at t was from the event at t that it was from the n of t process will have probability lambda of t over lambda of t plus mu of t. So n star of t will experience an event when either an event happens in n of t or m of t. What's the probability that the event that happened came from n of t? Well, that's lambda of t over lambda of t plus mu of t. So this is a very interesting result as well. But I think the most interesting is that if n of t and m of t are both non-homogeneous Poisson processes that are independent of one another, each with intensity lambda of t and mu of t, their sum is also a non-homogeneous Poisson process with intensity equal to the sum of the two intensities. I'll stop here. I'm not going to go further and actually discuss the non-homogeneous Poisson process. I just want you to know it exists. And it's the first step in generalizing from stationary increments to non-stationary increments, or from homogeneous increments to homogeneity in time, in other words, because that's what stationarity is. It's homogeneity in distribution in time, right? So generalizing from homogeneity to non-homogeneity, all you have to do is basically to just let this lambda, this rate at which an event occurs in an interval of length h, to be lambda of t times h instead of just a constant times h. Okay. So now let's move on to chapter 10. And the first thing we're going to talk about is the Brownian motion process. So let's go to chapter 10. So let us start by considering the symmetric random walk, which in each time unit is equally like to take a unit step either to the left or to the right. So it's a Markov chain with the probability of going from I to I plus 1 is 1/2, and it's the same as that of going from I to I minus 1 for any I, 0 plus or minus 1 plus or minus 2, etc. So now suppose that we speed up this process by taking smaller and smaller steps. So if you so this is what happens, right? In the random walk model, basically, what happens is the time goes up in 1 unit, in units of 1, okay? And then the space goes up by 1 or down by minus 1 each time. So, you know, you basically bounce around on the integers at each point in time t, right? So at time, say you start at 0, then your perhaps are going to go to 1, then perhaps you're going to go to 2, then you're going to go back to 3, etc. So this is one of the possible paths of the random walk, which is of course a Markov chain, as we see with these transition probabilities. Now, what you do instead in the Brownian motion model is that you take the interval, say 0 to 1, and you divide it into smaller intervals of length delta t, each of length delta t. So at time 1, instead of having made one step forward, you have made however many delta t's are in 1, right? So 1 over delta t. So if the number of steps that you have made to obtain, to get to 1 is 1 over delta t. So say if delta t is 1/10 of the interval, then you need 10 units, 10 ups or downs to get to time 1, right? So what you do is you decrease time, you take a step of size delta x, okay, either to the left or to the right with equal probabilities at each point in time delta t. So if we let x of t denote the position at time t now, what is it going to be? It's going to be delta x times x1 plus x2 plus and so on, right? Plus and so on, plus x integer part of t over delta t. So for any given t, so where xi's are what? They're IID, the xi's are IID, 1 or minus 1, each with probability 1/2. Okay? So the xi's are basically the random walk steps, okay? They're either 1 or minus 1 with probability 1/2. And every time you move by x1 or x2, so 1 or minus 1, you really don't move by 1 or minus 1. You move by delta x each time. And then at each point in time t, how many such steps have you taken? You've taken t over delta t. So at time 1, you have actually taken 1 over delta t steps. So at time t, any time t, you have made t over delta t steps. If t is an integer, then you don't need the integer part. If t is some general number, then you need the integer part. But the bottom line is that the x of t, as we can see, is a sum of IID Bernoulli random variables. So these are, the xi's are IID, Bernoulli random variables. So of course, if you want to look at the distribution of an object like this, the first thing that comes to mind is the central limit theorem, because it's a sum of IID random variables. So the moment you start thinking about whether I actually get a limit that makes sense, and you want to find what is the distribution of that limiting random variable, the first thing that comes to mind is the application of the central limit theorem. But then again, one has to make sure that you scale time and space in such a way that the resulting random variable is actually a non-degenerate random variable, and it's something that we could potentially be talking about the distribution of, right? So you need to scale delta t and delta x in such a way that this limit actually makes sense and exists and is interesting to study. Okay. Now, what's the expected value of each of these xi's? Well, it is equal to 0, excuse me. It's 1 times 1/2 minus 1 times 1/2. That makes 0. What about the variance of the xi's? Well, the variance of the xi's is the expected value of the xi square minus the expected value of xi all square, but that's a 0. So the expected value of xi square is 1 squared times 1/2 plus minus 1 squared times 1/2, and that just makes 1. Okay, so now if we want this guy to have a limiting distribution that makes sense, it's got to have an expectation that makes sense and a variance that doesn't explode or doesn't go to 0, right? Otherwise, we can't be talking about its limiting distribution. So let's look at what is its expectation. Well, it's a sum of IID random. It doesn't matter if they're IID, but it's a sum of random variables which are centered at 0. So clearly, itself is going to be centered at 0. So the expected value of x of t is going to be identically equal to 0. Now, what about the variance of x of t? Well, the variance of x of t is just going to be, well, this constant square, delta x square, times the sum of the variances of the xi's, since the xi's are independent, identically distributed, and that variance for each of the xi's is 1, so you're adding 1 plus 1 plus 1 plus 1, t over delta t times integer part of that. But you don't really have to worry about the integer part. You can think of t as being an integer and then everything works out just fine. But basically, this is the scaling that you get for the variance of x of t. Now, look at this variance. If I let delta x be, say, in the order or vary in the order of delta t and let delta t go to 0, what am I going to get? I'm going to get something that's identically equal to 0, right? Because this is going to be delta t square over delta t. The t doesn't matter, it's just a constant. So that's the order that you're going to get. And if you take the limit as delta t tends to 0, in that case, what you would get is something that's 0. So, well, there's nothing interesting about a random variable with an expectation of 0 and a variance of 0. So it's not an interesting quantity to study if I scale delta x in the order of delta t. If, on the other hand, I say scale delta t, say if I scale, I don't know, let's think about this. If I say scale delta t in the order of, say, delta x cubed or something, then I'm going to get the denominator to be going to 0 faster than the numerator, and then I'm going to get the variance to explode, so that also doesn't make sense. So the only way I can get a variance that actually has a limit that's a constant of some sort is by letting, so you've got to let delta x vary in the order of the square root of delta t. So you can set it to be some constant times the square root of delta t. And if you do this, you're going to end up with something that looks like this, sigma delta t divided by basically something that's in the order of delta t. So these two are basically going to cancel effectively when you take the limit. And what you're going to have is that the limit of x of t, because in the end, what do? You end up, you scale time and space into smaller and smaller intervals, and what do you want to do in order to get the limit? You basically want to scale down as much as possible. Scale space, scale time down to 0, but in such a way that the limit makes sense, right? Is non-degenerate. So your objective is to let time delta t go to 0 and delta x go to 0, but in such a way that the limit exists. So when you let scale delta x in the order of square root of delta t, what you see is that you get same order in numerator and denominator. So you can actually take the limit as delta t tends to 0. And when you do that, basically you obtain a constant, and that's basically, well, let's see. So this would be, so this is sigma square, so this would be sigma square. This would be sigma square t, sigma square t. That's it, right? So the limiting, I apologize, this is wrong. It's the limit, not of x of t, obviously, it's the limit of the second moment of x of t. That means of the variance, well, of the variance of x of t. So this is the limit as delta t tends to 0 of the variance of x of t. It's sigma square t. Okay, so the limit of variance of x of t as delta t tends to 0 is equal to sigma square t. Okay, so now you have the expected value of x of t equal to 0. The variance of x of the limit of the variance of x of t as delta t tends to 0 is sigma square t. And okay, so you know the expected value, you know the variance, and you know something else too, that x of t is the sum of IID random variables. So now you can tell me something about the limiting distribution of it. In fact, you can define it exactly, because by the central limit theorem, the law of this guy is going to be normal by the CLT, normal, with mean 0 and variance sigma square t. And since any random variable that is normally distributed is entirely defined by its first and second moment, now you know absolutely everything about the distribution of x of t. So this gives rise to, well, what exactly is a Brownian motion? Let's try to think about this for a second. Okay, we can see it as the limit of a random walk if we scale time and space appropriately and take smaller and smaller time intervals and smaller space displacements. Okay, we can see that. But what do we really actually get? So for any t, x of t will be normal 0 sigma square t. But if I were to actually draw a graph of this x of t from 0 up to t, what kind of a picture would I see? And it turns out what you see is something that is everywhere. It's a function, as a function of time. It's a function that is everywhere continuous and nowhere differentiable. Now, can you imagine a function that is everywhere continuous and nowhere differentiable? If I were to draw a simple path of it, I should start with my pen, drawing its path, and I should never take that pen off the board since it's continuous. That's what continuity means. But it's nowhere differentiable, so it's got to be crooked absolutely everywhere. So it's a very hard thing to draw because I can't draw something that's crooked absolutely everywhere, but I can definitely draw something that's continuous everywhere. All I have to do is the moment I start drawing, never take my pen off the board again. But this is what a simple path of a Brownian motion more or less would look like. Very crooked, but everywhere continuous. You see? This is what the resulting path of a Brownian motion is like. So this is what it would look like from, say, 0 to t. This is x of 0, this is, say, x of s, whatever it is, and this is x of t, etc., right? And this is everything wherever it's been in between. Now, there's several properties that we can extract out of basically its very construction. And we're going to look at them one by one. So the Brownian motion, as a matter of fact, so let me just give you some historical facts. Well, a couple of things. So x of t is normal with mean 0 and variance sigma square t. In addition, because the changes of value of the random walk in non-overlapping time intervals are independent, we will have independent increments. So if we look at, say, x of tn, minus x of tn minus 1 for the interval tn minus 1 to tn, and let's say x of tn minus 1 minus x of tn minus 2, etc. I can go on to 0, of course. What are they going to be? They're going to be dependent. Why? Because the x's that are going to be added from the interval tn minus 1 to tn are going to be independent from the x's that are going to be added between the interval tn minus 2 to tn minus 2, that's right, to tn minus 1, etc. So indeed, we're going to have independent increments. We also will have, what we will have is stationary increments, because the distribution of x of t plus s minus x of t does not depend on t, okay? So you can see that from x of t to x of t plus s, you're adding some xi's. Xt, you know, from xt all the way to xt plus s, you're going to add some xi's. But the distribution of those xi's is going to be the exact same one regardless of where you start counting them. That means no matter which t you start from, you are always going to be adding IID Bernoulli random variables and scaling them appropriately and taking their limits, right? So indeed, the distribution of x of t plus s is independent of t. Independent of t. This means independent. Independent of t. So therefore, you have stationary increments. And this gives about a nice definition for what Brownian motion is. So, and then I'm going to discuss where it came from, where did people actually observe it for the first time, and when did they start studying its properties. It was actually observed as a particle immersed in a liquid. So what kind of a motion does it have? It is immersed in a liquid. It was observed by a botanologist called Robert Brown at the beginning of last century, that basically immersed a particle in some medium, and it was receiving collisions from all sides. And so its motion was very erratic, looked like this. And so that's where the name Brownian motion came from, okay? But then it wasn't until later that its properties were described mathematically and studied mathematically and became more rigorous. And this was done by Wiener a few years later, a couple of decades later than Brown. And so that's why the Brownian motion is also known as the Wiener process. Okay. Now, of course, it's a prototypical stochastic process on many forms. It's a Gaussian process, it's a martingale. We'll see what all that means. It has stationary and independent increments. It's got increments that are normally distributed. So, of course, it's prototypical in many ways and forms. But that's not its own. But the reason, so it comes into play in many fields. For instance, quantum mechanics is one of the places where it appears. It has appeared in financial mathematics to describe, say, stock price dynamics or interest rate dynamics, or you name it. It comes in stochastic differential equations. It comes, so for instance, you know, in physics. Anyway, so let me just give you a definition, a more formal definition. So a stochastic process x of t is said to be a Brownian motion if, so a stochastic process x of t is said to be a Brownian motion x of 0 is equal to 0 to x of t greater or equal to 0 has stationary and independent increments. And for every t, x of t is normally distributed, with mean 0 and variance sigma squared t. So yeah, so this is this historical stuff I was talking to you about. So, all right, so finally we come up with the definition of the Brownian motion. Starts at 0, has stationary and independent increments, and those increments are normally distributed. The Brownian motion process, sometimes called the Wiener process, is one of the most useful stochastic processes in applied probability theory. It originated in physics as a description of Brownian motion. This phenomenon, named after the English botanist Robert Brown, who discovered it, is the motion exhibited by a small particle which is totally immersed in a liquid or gas. Since then, the process has been used beneficially in such areas as statistical testing of goodness of fit, analyzing the price levels on the stock market, and quantum mechanics, as I told you. The first explanation of the phenomenon of Brownian motion was given by Einstein in 1905. He showed that Brownian motion could be explained by assuming that the immersed particle was continually being subjected to bombardment by the molecules of the surrounding medium. However, the preceding concise definition of this stochastic process underlying Brownian motion was given by Wiener in a series of papers originating in 1918. Now, when sigma is equal to 0, then the process is called a standard Brownian motion. Sigma is equal to 1, excuse me. It's a standard Brownian motion. Because any Brownian motion can be converted to the standard process by letting b of t be equal to x of t over sigma. So all you have to do is just divide by sigma. We shall, unless otherwise stated, suppose throughout this chapter that sigma is equal to 1. So just let sigma, without loss of generality, let sigma equal to 1. Now, the interpretation of Brownian motion as the limit of the random walk suggests that x of t should be a continuous function of time. We saw that it is. This turns out to be the case, and it may be proven that with probability 1, x of t is indeed a continuous function of t. But in order to prove that, that's actually a very deep proof. You need the construction of Brownian motion by using Haar functions. Okay, and so I'm not going to get into that. You actually need first year PhD probability to get to something like this, so I'm not going to get into it. As x of t is normal with mean 0 and variance t, its density is f sub t of x, so let sigma equal to 1 now from 1 on, so we can just let sigma equal to 1, then you have x of t is normal 0 t. Its density is 1 over root 2 pi t e to the minus x squared over 2t. To obtain the joint density of x of t1, x of t2, and x of tn for t1 less than tn, know first that the set of equalities x of t1 equal to x1, x of t2 equal to x2, and so on, x of tn equal to xn is equivalent to x of t1 equal to x1, x of t2 minus x of t1 equal to x2 minus x1, and x of tn minus x of tn minus 1 is equal to xn minus 1. Now you have independent increments, so x of t1, x of t2 minus x of t1, x of tn minus x of tn minus 1 are independent, and by the stationary increments assumption, x of tk, we have for each of those intervals, x of tk minus x of tk minus 1 is normally distributed with mean 0, tk minus 1. So the joint density of x of t1 through x of tn, then if I take the joint density f sub x1 through xn, then all you have to do is write it in terms of the product of the independent increments, and basically at f t2 minus, so in t, from t1 to t2, so f sub t2 minus t1 of x2 minus x1 times f of t3 minus t2 of x3 minus x2, etc. And then you have f sub tn minus 1 of xn minus 1. Okay, and what do you obtain? You obtain x1 squared over t1 plus x2 minus x1 squared over t2 minus t1 plus and so on plus xn minus 1 squared over tn. Okay, so this divides by 2 pi to the n half, and this is t1, t2 minus t1, tn minus 1, and this is the joint density of x1 through xn. In order to express it, you have to write it as the product of the densities of independent things, and what is independent in this case? It's the independent increments. So basically, this is the probability of being at x1 in t1 units of time. This is the probability of being at x2 minus x1. That means displace yourself by another x2 once you're in x1, right? So the increment of x2, the increment of the movement, which is x2 minus x1 in t2 minus t1 units, the increment of the change in position, again, now once you're in x2, which is x3 minus x2 in t2, in t3 minus t2 units of time, etc. And it's the product of these densities, each of which, each of these random variables, x2 minus x1, x3 minus x2, x1, all of those are independent, normally distributed random variables with these variance. So you can write the joint density in this form. Now we can compute, in principle, any desired probabilities. For instance, suppose we require the conditional distribution. This is an interesting one. So you're looking at the conditional distribution Okay. Okay. So suppose we require the conditional distribution of x of s given x of t is equal to b, where s is less than t. So the conditional density is f of s given t of x given b. Then what you will have, again, you're going to look at what? The independent increments. So you're going to go the position at s, and then the increment from x to b, right? In the rest of the time that's left, which is t minus s. So the displacement is b minus x. So this is the joint density of fst of x and b, right? So, but that's can be written as the product of two independent random variables. One is the displacement from 0 to s, the position at time s, which is x, and times the displacement going from x to b, so displacement b minus x, at the rest of the time left from s to t, so in time interval of length t minus s, divided by the density at b. What do you obtain? So let's write it down. It's going to be some constant k1 of exponential of minus x squared over 2s coming from this density minus b minus x squared over 2 times t minus s. This is coming from here, and f sub t of b is just a constant, so it gets absorbed into k1. Now what you can write, this is equal to, I can factor out x squared, and what will I have left inside? So some k2 if you like, so put all the constants in k2. If I factor out x squared, I will have inside 1 over 2s coming from this term, and I'm going to have so I have a plus x squared coming from here. So I'm going to have a plus x squared with a minus at the front, so minus x squared, and then I'm going to have a 1 over 2t minus s coming from the factor that's in front of x squared when I expand the square. So that's that. And then you will also have plus the linear term. And of course, you will have the term in b squared, but that gets absorbed into the k2 constant. But you have also the middle term, which is a minus 2bx cancels the 2. Okay, with a minus at the front becomes a plus. So you have a plus bx over t minus s. And that's right over here. So let's see what we can do next. We can basically do some calculation over here, and we will have t minus s plus s over s t minus s, right? So t minus s plus s, so this cancels with this, and I have a t over s, t minus s. Okay, so then I can rewrite this as some k2 doesn't matter, and then what you have a minus x squared, okay, you have a minus okay, you have a t over s, t over, so the 2s, t over s, t minus s. Now if you let that go outside, inside you're going to have an x squared, and then if you want the t minus s to go down there, and you want a t over s to be over here, you need to multiply this term by an s over t. If you're going to write it in a parenthesis, and you need a 2 at the front because you've divided by 2 over here. And so you've got a 2s over t b times x. Okay? And now you can, by adding and subtracting some constant in sb over t, so the square of sb over t divided by whatever needs to be divided by at, and then that you can actually incorporate in some constant k3. So you complete the square, and what you obtain is an exponential minus x minus bs over t whole thing squared divided by 2s t minus s over t. Okay. 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 So what does that tell me? It tells me that the conditional distribution of x of s given x of t is equal to b, then has an expected, is also normal, and of course it has the expected value b times s over t, so s over t times b, and the variance of x of s. So x of s given x of t equal to b is also a Gaussian random variable. It's a normal random variable with mean this and variance s over t, t minus s. So this is a nice, cool calculation. So heating times maximum variable in the gambler's ruin problem. So let's look at that. Okay. So let T8 denote the first time the Brownian motion hits A. So TA is the first time, so infimum over t greater or equal to 0. So the first time that x of the Brownian motion, x of t, hits A. So let's look at a possible path just so we have a graphic idea of what's going on. So say this is A, so the first time A is hit is this time, and that's TA. Okay. So when A is greater than 0, we will consider, we are going to look at this event, the probability of this event, by considering x of t being probability that x of t is greater or equal to A. So let's look at that. So let's look at that. So we want to look at the we want to find out what's the distribution of TA, of this random variable. This is the first time that the Brownian motion reaches the level A. Okay. So we're going to do that by looking first at this random variable and conditioning on TA less or equal to t and TA greater or equal to t, and see if we can obtain something interesting, right? So this is the probability that the Brownian motion, so this is x of t, it's the probability that x of t is greater or equal to A. Well, that can be written by the law of total probability as the probability that x of t is greater or equal to A, given that TA is less or equal to t, times the probability TA is less or equal to t, plus the probability that x of t is greater or equal to A, given TA is greater than t. Okay, so now if TA is less or equal to T, then the process hits A at some point in 0T, and by symmetry it is just as likely to be above A or below A at time T. Okay, so if TA is less than or equal to T, so if I let this be T, so this is the case in this graph, TA is less than or equal to T, the process hits A at some point in 0T. By symmetry it is just as likely to be above A or below A at time T. So in other words, this path has the same law as, say, this path, which is the symmetric path. You see? The symmetric. So to be below A is equal to basically being above A. The probability of ending up at time T, x of T, so we're here at x of T. In this case, it turns out to be below A. Okay, but it's equally likely to be above or below A once it hits A, because this path and its reflected path with respect to the line A have the exact same distribution. Have the exact same distribution. This path and this path have the exact same distribution because they're reflected versions of one another. So, the probability that x of t is greater or equal to A, given that TA is less or equal to T, is definitely equal to 1/2. Okay. So the probability that I end up above A, given that I hit A before time T, is equally likely to be above, so the process is equally likely to be above A as it is to be below A once it hits A at by time T. So that probability is equal to 1/2. Now, what's the probability that x of t is above A, given that it never hit A by time t? Well, that's just identically equal to 0, because if I haven't hit A by time t, then certainly I can't be above A at time t. Why? Because this process, the Brownian motion process, is continuous. So I've got to have hit A by time t for me to be above A at time t. Okay? So that probability is 0. And this probability is 1/2. So I obtain this is equal to 1/2 times the probability that TA is less or equal to T. So the probability x of t is greater or equal to A is equal to 1/2 probability that TA is less or equal to T. And that gives me that the probability, therefore, the probability that TA is less or equal to T, and so that's the cumulative distribution function of the random variable I wanted to study the distribution of. So that is now twice the probability that x of t is greater or equal to A, and I know exactly what that is because this is a Gaussian distribution, right? And I'm asking what's the probability a Gaussian random variable with mean 0 and variance t is above A. Okay, that's what I'm asking, and that's definitely something I know exactly, right? So then I will have 2 times 1 over root 2 pi t, A to infinity, e to the minus the kernel of the Gaussian distribution. Okay, so this is going to be this. Okay, so of course it is the case that if A is less than 0, now if A is less than 0, the distribution of TA is by symmetry the same as that of T minus A, right? So TA and T minus A have the same distribution. So by symmetry, just doesn't matter if A is above 0 or below 0. So really what you should be so this probability then should really be this, okay? So regardless of what is the sign of A, the probability is just integral from absolute value of A to infinity of e to the minus x squared 2t, which is the Gaussian kernel, twice 1 over root 2 pi t. Okay, Another very interesting random variable that's directly related to the first heating time, which is TA over here, is the maximal random, the maximum of the process. So let's look at that. So this is TA. It's the first time. Let's just write it down one more time. It's the first time that x of t is equal to A. So this is the first time the process hits A. But what can you tell me about how that relates to the maximum of the function? If I look at the maximum of x of s for s between 0 and t, well, so let's draw a graph of the maximum. This is what the maximum looks like, right? That's what the maximum looks like. I'm just taking the maximum in all this, right? So now, if the maximum between 0 and t is above A, then that says that that's equivalent to saying that by time t for the process has already hit A, right? So if the maximum of the process at time t is above A, has exceeded A, that means that by time t, the process has already hit A. Okay, so now, so what is this? This is, so if I take the probability of this event, well, that's the same as the probability of this event, but that is already, as we saw, twice the probability that x of t is greater or equal to A, and that we already have is 2 over root 2 pi t A to infinity the Gaussian kernel dx. Yeah? Okay, cool. So that gives me also the probability distribution of the maximum of Brownian motion, which is also a very interesting result because I have a closed form formula exactly for the survival probability of the distribution of the maximum of a standard Brownian motion. Okay. Now, let me see for 1 second. Okay. So we can consider now the probability that Brownian motion hits A before hitting minus B. So we start at 0, and we're looking at the probability that the Brownian motion hits A before hitting minus B. Well, that's just a random walk process, right? But now it's a limit of a random walk process where the space displacement, instead of being +1 or -1 each time, is actually delta x plus delta x or minus delta x. So what can we do in order to calculate the probability of hitting A before minus B? So the probability of hitting A before going to minus B. This is, I can, just sort of bring up everything by B units in this graph, and I will have, say, this being, say, what will it be? This should be, so starting at, say, I, what's the probability of going up to A, so A plus B, n, going up to n, where this would be A plus B over delta x. That's how many units I would need to get to, right? And I'm starting, say, at B over delta x, and I'm asking what's the probability of hitting A plus B, so running up by A plus B, so this many units, before reaching 0. So this is the Gambler's ruin problem, where you start at, say, so imagine now this interval is divided by delta x all the way. You bring it up by B units, so this becomes A plus B over delta x, and 0 becomes B, but B over delta x because it's divided in delta x units. And you're asking what's the probability in a Gambler's ruin problem where the random walk process is what's in effect. What's the probability I reach n, right, my target wealth, before going broke? But that I know already, and that's just the probability of up by A before down by B. So that's the gambler's ruin problem. And that's the same as basically calculating the gambler's ruin problem with above limit, so numerator b over delta x, denominator a plus b over delta x, but this cancels this out, so you obtain b over a plus b. And that's done, okay? So you actually can calculate the probability of going up by A before going down by B. So now we can look at variations of Brownian motion, of course, and I will do that next. But before doing that, I'm going to tell you a little bit what the martingale is, which is actually not in your book, but it's an interesting and important class of stochastic processes, the martingales. Martingales are stochastic processes that are constant in expectations. And then there is sub-martingales that increase in expectation, and then there is super martingales that decrease in expectation as time goes on. But the most interesting ones are, of course, the martingales, which are constant in expectation. And of course, I will argue, since Brownian motion is the prototypical example of a process, it's not just a Gaussian process, it's also a martingale, and it's got independent and stationary increments. And it's continuous paths as well. So it's a prototypical type of a process in many ways. But let me talk about what a martingale is now. This is something you won't find in your book. So let me just erase all this. Okay, so what's a martingale? So a martingale is a stochastic process x of t, such that when you take the expected value of x of t given x of s for s between 0 and t, okay, you obtain x of s. So that means the best guess of where the process is going to be at time t, given that at time s, so actually I should say it like this. S is less than or equal to t. So take s less than or equal to t. So your best guess, well, given the whole path as a matter of fact. So s between zeros, let's just say this, like that. So for s greater or equal, so given the whole path of where it's been from 0 to s, the best guess of where it's going to be at time t, which is ahead by t minus s units from s, your best guess of where it's going to be in the future, given where it is today, is where it is today. That means it's constant in expectation. So let's see, it's Brownian motion, a martingale. So this type of a process is known as a martingale. Okay, constant in expectation. Now let's take Brownian motion. The expected value of x of t given x of s, so if x of t is Brownian motion, then we have the expected value of x of t given x of s for s greater or equal to 0 is just going to be now what? The expected value of x of t minus x of s plus x of s given x of s, given I have observed the path of the Brownian motion between 0 and s. What am I going to again? This is going to be the expected value x of t minus x of s plus x of s. So what is that? So let's write it down. Plus the expected value of x of s given x of s between 0 and s. What do you obtain? So now the first expectation is going to be, this is the increment from x of t to x of s, so from x of s to x of t, so the increment x of t minus x of s given x of s. What is that going to give me? Well, I have independent increments, so where the processes at time s will not affect what happens to the increment x of t minus x of s. So I will obtain the expected value of x of t minus x of s without the conditioning since I have independence. And now here I'm asking you, what's x of s given x of s? Given the whole path from 0 to s. Well, wherever it is at s, that's where x of s is going to be, right? So this is definitely x of s. But what's the expected value of x of t minus x of s? Well, I already know that all the increments in a Brownian motion are normally distributed with mean 0 and variance t minus s. So this expected value is identically 0. So what do I get? I obtain that indeed I have the martingale property, because the best guess of where the position of the particle is going to be at time t given where it's been between 0 and s is exactly where it is at time s. Okay, so that's that. Okay, so that's a martingale. So now that I know what a martingale is, I can go and generalize Brownian motion and look at when do I get a martingale and when do I not. Okay. So the variations on Brownian motion. So Brownian motion with drift. We say that x of t is a Brownian motion process with drift coefficient mu and variance sigma square if so x of t is normal nu t variance sigma square t. Okay, if basically one x of, so this is a x of t is a Brownian motion with drift mu and variance sigma square when the following holds. Starts at 0, it has stationary and independent increments. X of t, as usual, has stationary and independent increments. and x of t is normally distributed with mean mu t and variance sigma squared t. Okay. So you can think of it as being, if you take a standard Brownian motion, so if you let b of t be a standard Brownian motion, you can write x of t as sigma b of t plus mu t. And let's see if I can actually draw a path of such a process. It's actually very easy to imagine what a process like this was going to look like. Let me just, so what's happening? This is a Brownian motion, except it's centered at mu t, and it has a variance of sigma squared t. So what does it do? It basically behaves as a Brownian motion, but not centered in the x-axis, centered in around the line mu t. So effectively, what a sample path of this would look like if I make, say, the line, if I draw the line mu t, okay, and I try to draw a path of x of t, a possible path of x of t, then it would be centered around mu t. Again, it would be continuous everywhere, differentiable nowhere, right? So it's going to basically look more or less like this. Of course, any value is possible, but you have this centeredness around mu t. As you seen before, when you had the standard Brownian motion, you were centered around 0, because you had an expectation which was equal to 0. But now you have a Brownian motion with drift, equal drift mu t, constant drift mu t. Okay, so you're basically centered around the line mu t. Yeah. Okay. So that's one, the sort of easiest generalization of a Brownian motion. That's it. Now, another generalization of the Brownian motion is so-called the geometric Brownian. So this is a Brownian motion with drift. Let's look at the geometric Brownian motion. So give me one more time, where basically the process is e to the y of t, where y of t is a standard Brownian motion or a Brownian motion with drift, doesn't matter. And your x of t is e to the y of t, and so its logarithm is a Brownian motion. So that's a geometric Brownian motion. So you might use it, for instance, for asset prices where the asset prices are not supposed to ever go negative, right? So a possibility is the exponential Brownian motion, or the geometric Brownian motion process for such a model of stock price, which is actually very much used in what's one of the prototypical models used in financial mathematics to describe stock price dynamics is the geometric Brownian motion. Okay. So the geometric Brownian motion okay. Okay, so if y of t is a Brownian motion, so if y of t is a Brownian motion with drift, mu, and variance sigma square, then the process x of t is defined by okay. This type of process is a geometric Brownian motion. So it's a Brownian motion, so this is a drift, so y of t is a Brownian motion with drift mu and variance sigma squared, like what we saw before. Then x of t equal to e to the y of t is a geometric Brownian motion. So that means the logarithm of x of t, which is y of t, is a Brownian motion. So if the logarithm of x of t is a Brownian motion, then x of t itself is a geometric Brownian motion. So for a geometric Brownian motion process, let's compute the expected value of the process at time t given the history of the process up to time s to determine, for instance, if it's a martingale or not, right? So we consider the expected value of x of t given x of u, so given the whole path for u between 0 and s is what we did before, basically. So this is the same as the expected value of e to the y of t, given now, whether I give you x of u for u between 0 and s, so the whole path in terms of x, or I give it to you in terms of y, it's the same thing. All you have to do is take the logarithm of one and you will get the other. So I give you the x's or I give you the y's between 0 and s is exactly the same thing, right? So I can write this as e to the y of t given y of u between the whole path in terms of y between 0 and s. Well, all I have to do is now write everything in terms of increments. Why? Because the increments of Brownian motion are independent, so I can work with them in a much easier way. And so this is okay. Okay, so now, so what do we have? So then you have the expected value of e to the y of s times e to the y of t minus y of s given y of u between 0 and s. But since you have independent increments, the expected value of e to the y of s, e to the y of t minus y of s will be the expected value of e to the y of s given y of u from 0 to s. And times the expected value of e to the y of t minus y of s given y of u between 0 and s. So you will obtain the expected value of e to the y of s given y of u for u between 0 and s times the expected value of e to the y of t minus y of s given y of u for u between 0 and s. Okay, so now what's e to the y of s if you give me where the path has been between 0 and s? Well, it's exactly where it is at s, so it's e to the where it is at s, so this just becomes e to the y of s. And what is this? This increment is independent of y of u between 0 and s because you have the independent increments property. So you obtain times expected value of e to the y of t minus y of s. Okay, so this is e to the y of s times expected value of e to the y of t minus y of s. Okay, well, what is this? What's the expected value of e to the y of t minus y of s? What's y of t minus y of s? It's a normal random variable with mean mu t minus s and variance sigma squared t minus s. And what is this? This is effectively the moment generating function of a normal random variable with this mean and this variance, evaluated at t equals, at a, let's say, equal to 0. So let's just write this down. So if I take a normal random variable and calculate e to the aw, so where w is normal with some mean expected value of w and some variance, the variance of w, then the expected value of e to the aw is e to the a expected value of w Okay, so what do I obtain? So I obtain e to the y of s, expected value of e to the y of t minus y of s. So this is just going to give me e to the, well, so take a equal to 1, then I will have expected value of w, but that's just e to the mu t minus s, e to the y of s times e to the mu times minus s plus a, but now a is 1, so 1 square variance of w, that's just sigma square t minus s over 2 plus sigma square t minus s, and I have the over 2 over here. And so what I obtain is that's the same. What's e to the y of s? That's just x of s. And then I have an e to the t minus s times mu plus 1/2 sigma square. So is x of t, which is a geometric Brownian motion, is that process a martingale? Certainly not, because its expected value of x of t given its history from 0 to s is not equal to x of s. It's x of s times a number that's actually greater than 1. So as a matter of fact, the best estimate of where x of t is going to be, given where it's been between 0 and s, is not x of s, but it's something above x of s, right? So it gets sort of, expectation gets, so this process gets larger in expectation. So what it is actually is, actually a sub-martingale. Okay, so that's the story. So it's not a martingale anymore. So geometric Brownian motion is not a martingale. Now, where does it come into play? As I told you, it can be used as a model to describe asset price dynamics. It's a prototypical model that's been used in financial mathematics. But let's look at it in terms of what your book describes. All right, so basically, geometric Brownian motion is useful in the modeling of stock prices over time when you feel that the percentage changes are independent and identically distributed random variables. So for instance, suppose that xn is the price of some stock at time n, then it might be reasonable to suppose that xn over xn minus 1 are independent and identically distributed. Okay. Geometric, okay, so suppose that, so xn, suppose xn is the price of some stock at time n, price of some stock at time n, okay, then it might be reasonable to suppose that xn over, so these are the percentage changes, are independent, identically distributed. And so if you let yn to be xn over xn minus 1, then you can write xn as yn times xn minus 1, and then by induction you can write then xn minus 1 would be yn minus 1 times xn minus 2, and so on. And then you can okay, so thus the logarithm of xn is equal to the sum I going from 1 to n of the logarithm of the yi's plus the logarithm of x0. Okay, so since the logarithm of the yi are independent and identically distributed, log of xn will, when suitably normalized, be approximately equal to a Brownian motion with a drift, and xn will then be approximately a geometric Brownian motion, right? Because its logarithm is Brownian motion with drift, effectively, or if you like, random walk, and if you take the limit, it becomes a Brownian motion with drift. So if its logarithm is a Brownian motion with drift, then itself is a geometric Brownian motion. So this is a nice model for to model percentage changes. Okay, that's that for lecture number 11 of STAT 702.